Hello everyone, my name is Yihan Zhang from Columbia University. Today I am going to present my project in the course ELEN6350 VLSI Lab. This is a low noise current amplifier IC fabricated in 130 technology provided by MOSFETs. Before moving into the engineering details, I would like to talk about the motivation behind this chip first. Electrochemistry is a branch of chemistry where electrical stimulations were applied to a chemical system, and the chemical properties could be read out by corresponding changes in the electrical signals. One of the useful tools in this area is called voltammetry, where voltage stimulation is applied and the current signal carries information of interest. However, in biological systems, chemicals of interest are usually in very low concentration, which provide a low current signal down to picoamp level and sometimes femtoamp level. Thus, a current amplifier, or a transimpedance amplifier that is capable to detect very low current level, is needed. And noise performance is one of the most important metrics in determining the lowest detectable signal. The topology of the transimpedance amplifier is chosen as a current integrator. How does it work? Well, take a look at this schematic. When the switch is closed, the OTA is under unity gain feedback, and the voltage across the capacitor is zero. Input current won't produce any voltage change if the switch is ideal. Let's see how the capacitor integrates the input current and produces an output voltage when the switch is open. Say at time 0, the switch opens, and the input current is a constant value In. During a very short time of delta t, the current sees the capacitor and accumulate charge. The amount of charge on the capacitor is In times delta t. If the voltage at the inverted input of the OTA goes up a little bit, then the output will swing all the way down, since the amplifier has a huge gain. However, the amount of charge at the capacitor is fixed, and so does the voltage across the capacitor. Therefore, almost all the voltage drop will happen at the output, while the input is held approximately at the bias voltage VB as long as the output doesn't reach the limit. And the output voltage now is VB minus In times delta t over Cin. Two more stages are used to help amplify and sample the signal, which I will not talk in detail here. If you are interested, please take a look at the web pages where more information is available. In order to make the transimpedance amplifier able to work for chemicals with different redox potentials, the input voltage range of this amplifier needs to be wide. As all the OTAs in the design work under closed loops, the output range of all the OTAs need to be wide as well. In this chip, a rail-to-rail input-output amplifier is designed. By saying rail-to-rail, it means the amplifier can work with whatever input and output voltage as long as it's between the high and the low power supply voltages, which are commonly referred as rails. This is a schematic of the OTA without bias circuits. It can be broken down into three parts. The first block utilizes a combination of NFETs, which work at high input voltage, and PFETs, which work at low input voltage, to generate constant transconductance against the input common mode voltage. The second block sums up the signal from the first block, which is carried by 4 wires, into one signal runs on a single wire. The third block is a Class AB power amplifier biased in subthreshold, so that the output voltage can reach the rails without too much gain loss in comparison to the gain in the middle of the rails. In order to test the performance of the chip, a printed circuit board, or PCB for short, is designed and fabricated. There is an FPGA to generate all the control signals the chip needs. Besides the PCB, all these bulky equipment are also needed in prototype level testing. A computer program is written to automatically control the testing process. What you see now is the input and output waveform of the rail-to-rail input-output OTA we mentioned before, configured as unit gain buffer. The input signal is a 1.2 volt peak-to-peak sine wave, and the output only has about 10 millivolts drop in the amplitude. Now you are looking at the output waveform of the current integrator-based transimpedance amplifier, with a 20 picoamps amplitude, 10 Hz sine wave current as its input. The output voltage is about 200 millivolts in amplitude, which means the current integrator with this configuration has a transimpedance gain of 10 gigaohms. Before the end of this video, I want to thank Moses for offering the great opportunity taping out the chip using this advanced technology. I want to thank the EE department for the support in PCB fabrication related costs. And I want to thank Professor Peter Kingat for offering this course and his guidance through this tape out. I want to thank the TAs Young and Vivek for their help through this semester. Finally, and most importantly, I want to thank my advisor Ken Shepard for his support, and the other students in the Bio-E lab for their helpful discussions.